So, where can an RDD load its data from? Spark can handle numerous input sources. We've already seen loading from a file system, and of course, it handles distributed file systems such as HDFS or Amazon S3. Simply change the file path from file:/ to HDFS:/ or S3N:/ or whatever other type you're pointing at. Then there's databases, again also handling distributed ones like Cassandra. Even loading from memory is capable, if the data is able to fit from the start. Also, file formats aren't much of a problem, covering Parquet and Avro to name a couple. And all of these are just a subset of the possibilities. If you can store it, there's a good chance Spark can load it. But enough with the abstract. Let's see the methods that allow this in action. We're back in the shell, as it provides us the quickest feedback to play around with the parts of the API, especially those calls that load up from memory. Spark Context is the starting point for loading data into an initial RDD. So here, we use a method called parallelize to distribute a range sequence from 1 to 100. And if we collect this back to the shell driver, we can see the sequence as expected. Note that the ordering is retained, as RDDs keep ordering when able. We can see the method signature for parallelize by hitting tab twice, once for autocomplete, the second for the method signature. Here we see parallelize takes any sequence as we just saw, but also takes a parameter to override the number of partitions. This is an optional parameter which can be found in almost every RDD loading method. If not supplied, it uses the default parallelism, which in our case of using a local default shell is the total number of cores. If you don't prefer the parallelize method name, you can always use makeRDD, which does the same thing under a different name. MakeRDD also has another signature for setting up an RDD with suggested partitioning locations that we won't be using in this course. Now, while parallelize and makeRDD can handle any sequence, our example of passing in a range has its own method, shockingly named range. Both yield the same result, but range is built for this scenario, even having a parameter for the size of the steps that the range takes, which is defaulted to 1. That's all of the memory loading methods, but in a typical application, you're going to want to load data from an external source. We've already seen the text file method, which breaks the file down into lines, but at times, there's a need to read an entire file in so that it can be parsed as a single object instead of an object per line. Or, I've seen a number of cases where you need to know the file name that matches the document being parsed. That's where the whole text files method comes in. It's similar to text file, except the path it accepts is a directory path so that it has the potential to load from more than one file, even accepting wildcard paths. But often, data comes in a key value format, which is why we've imported the Hadoop I/O namespace, so that we can make use of its writable classes to be used in loading sequence files, a specialized key value format built for parallelism. This method accepts the path of our file as normal, but then it accepts two class types, the first being the type of the key's representation, and the other being for the value. These types need to be an extension of the writable contract. If you're ever trying to figure out what the writable equivalent for your type is, the suggestion is to append writable to your type name and see if it already has a representation. Otherwise, you might need to implement it yourself. A quick note on these types though. It's a good rule of thumb to load the data and immediately map to a native type. This avoids problems with serialization and other potential pitfalls surrounding the way Hadoop reads data. However, we can possibly avoid that whole rigmarole. Notice that there's a method definition that takes native type parameters, making it so that the method only requires the path. Using this signature results directly in the same type as our combined load and map, yielding the same results. If you want an easy null-keyed sequence file, you can use object file. However, its only benefit is the ease in which it can be created. It's a brittle format, breaking if the class changes at all. Even the official documentation seems to steer against it, saying that the format is experimental and may be removed in future versions. Although the method itself is not marked as experimental. But still, use it at your own risk. Now, all those file loading methods are really just wrapper methods around a more generic method, Hadoop file, that handles any Hadoop supported file format. This method takes the key and value type, similar to what we saw with the sequence file method. And the only additional parameter that provides the generic flexibility to handle anything is the definition of an input format type. Note that early on, the Hadoop API changed, which led to two APIs, referred to as the old API and the new API. Up until now, everything we've seen uses the old API for fuller support. However, if you are able to use the newer Hadoop API, then all you have to do in Spark is prefix the original API's method name with new API. These methods are practically duals of each other from a usage perspective. The only difference is that the new API methods don't accept a partitioning hint, but do optionally accept a Hadoop configuration to override the existing one already built by Spark. There's one last, even more generic method, which we'll use to start our text analysis project, and that's Hadoop RDD. The only difference between Hadoop file and Hadoop RDD is that it doesn't take a path, because the input format doesn't have to be and isn't assumed to be a file. Instead, both old and new API versions accept a Hadoop jobconf, which is expected to be configured for the particular input being loaded. Combine that with the flexibility of the input format, and that's how a number of different sources are able to be supported. In our particular case, we need to use Hadoop's Stream XML record reader, as the Wikipedia data dump is one continuous XML file with separate page nodes. And the XML stream reader allows us to split this document into parallelizable chunks. All we have to do is set up our Hadoop configuration and pass it into Hadoop RDD. Then declaring the use of the stream input format and an expected textual output. Note that we're using a subset of pages for our local testing. All the pages marked as big data. Our build.sbt also needs to add the Hadoop streaming dependency, as it isn't part of the standard Spark packaging. Make sure to use the same Hadoop version as you chose when picking your Spark distribution, or else you'll potentially run into dependency collisions. And now that we'll be using non-Spark dependencies, we'll need to create a jar file containing those dependencies, often referred to as a FAT or Uber jar. We accomplish this in SBT through the SBT-assembly plugin, which we configure to set up the jar name to be our project name and version, -separated. More importantly, we set up the packaging to not include Scala as it's already packaged as part of Spark. To enable this plugin, create an assembly.sbt in the project folder, specifying an SBT assembly dependency string which matches your version of SBT. SBT Assembly's API has been improving over time, so if you're using SBT 0.13.5 or older, then you should head over to SBT Assembly's GitHub page just to verify your setup for that version, as it might be slightly different. Before we close out this section, one final note on Spark's ability to load outside sources. Much of what's built in does create a tie-in to Hadoop that some sources don't want or need, so it's worth checking spark-packages.org or Google to see if there's a Spark connector which makes loading methods more native, negating the need to use Hadoop RDD, like the DataStax Cassandra connector.